Hello. This video is about the fundamental theorem of calculus. That's a very grand sounding title for a statement, a theorem, and it is a particularly grand theorem. And what I want to do today is to show you how this is actually a very natural and easy to understand statement, but it does give us a very useful insight into the relationship between differential and integral calculus. So we're back to water in the pipe. Suppose we have water flowing through a pipe, and once again we have a gauge which is sitting on the side of the pipe, which allows us to measure the rate at which the water flows. So we're getting our water from the municipality. They've put a flow rate gauge on our pipe, and that is going to calculate a total value, which is what we'll be charged for. There actually are two ways we can get the total flow, and one of them we've looked at by using numerical methods from the rate of change is one way we can do it. The other way is that we could just put a bucket at the end of the pipe and collect the water when it comes out. And these two methods of calculating the total flow must give us exactly the same value. So our perfect approximation, the integral from a to b of f of t dt, is built from the flow rate by taking infinitely many measurements of infinitesimal length. So if we kept going back to this meter and read out the rate of change infinitely often, then we would be able to get a perfect approximation, and that would be what we would get for that integral. So the perfect approximation is actually the limit of all the imperfect approximations. And when you study the the logical foundations for calculus, what you do is you make that statement rigorous, and you actually set up a limit process that takes you from approximations to the total flow to a perfect description of the total flow in the limit. So we can get a perfect approximation by calculating the value of this integral. And the other way that we can calculate it is that we can just put a bucket at the end and calculate and look at the way the water goes up in the bucket. So to introduce some notation, suppose g of t is the volume of water in the bucket at time t. Then the volume of flow between the times t equals a and t equals b is simply g of b minus g of a. That is the change in the volume of water in the bucket, and that will be an approximation. That will be exactly the amount of volume that flows through the pipe. So what we've worked out here is that the flow rate is the rate of change f of t of the water in the bucket. And the fundamental theorem of calculus says that if the flow rate f of t is the derivative of g of t, so f of t, what we measure on the meter, is the derivative of the height of water in the bucket, then the integral from a to b of f of t dt can be calculated as g of b minus g of a. This is the fundamental theorem of calculus. And it says that if we start with f and we can find a function g of which it is the derivative, so the derivative of g is f, if we can find that function, we can evaluate the integral from a to b of f of t dt as g of b minus g of a. And that is the fundamental theorem of calculus.